Hello students, welcome to your mathematics class. Today in this video, you will learn about the chapter matrices. In this video, my discussion topic is symmetric and skew-symmetric matrices and some related properties. Now what is symmetric matrix? Look at here. A square matrix A is equal to Aij is called a symmetric matrix if and only if A transpose matrix is equal to A matrix. Now we have already learned what do you mean by transpose of a matrix. Transpose of a matrix A is obtained from a matrix A by interchanging its rows into columns. Now let's see another definition of a symmetric matrix. If the element in the ijth position of a square matrix is same as the element in the jith position of the same matrix, then that square matrix is a symmetric matrix. So, if A equal to Aij be a square matrix such that Aij is equal to Aji for all I and j. So, in that case, we can say that the ijth element of a matrix A is same as the ijth element of the A transpose matrix. This is by definition of transpose of a matrix. And we know that two matrices are said to be equal if their corresponding elements are equal and their orders are same. So, we can say that A matrix is equal to A transpose because both are square matrices of the same order. So, these two matrices are same. And if A is equal to A transpose matrix, then that matrix A is called a symmetric matrix and it is a square matrix. Now let us see some examples of symmetric matrices. Now let us see some examples of symmetric matrices. Look at here. Here one example is shown. In this matrix, the first row elements are A, H, G. The second row elements are H, B, F. Third row elements are G, F, C. Now here if we find out the elements in the position A, 1, 2, which is here H, and which is same as the element in the position A, 2, 1, which shows that the element in the ijth position is same as the element in the jith position. Also, if we see the position of the element A13, which is G here, and which is same as A31. And also, here we can see that A23 element is F, which is same as A32. Now, let us find the transpose of this matrix A. Now, how we get the transpose of the matrix? By interchanging the rows and columns of the matrix A. Now let us write down the transpose of this matrix. So A, this is the first column. So we will write in the first row. So A, H, G. Then second column becomes second row. So H, B, F. And third column becomes the third row. That is G, F, C. Now after writing this A transpose matrix, let us compare with the A matrix. We can see that AHG, AHG, HBF, HBF and GFC, GFC. So both are same. That means A transpose matrix is equal to A. In this case, whatever the matrix A is given, which is same as the A transpose matrix. So this matrix A is called a symmetric matrix. Now let us try to construct ourselves a symmetric matrix. For example, let us write a matrix whose first row elements, any three elements we will write in the first row. Suppose 1, 3, 5. So this is the position 1, 1 position. This is 1, 2 and this is 1, 3. Now we know that 1, 2 is equal to 2, 1. The elements in the 1, 2 and 2, 1 positions are same. So here also we will write 3 and this 1, 3 becomes 3, 1 position. Both elements are same. Now this position is A22. So if you reverse this A22, 2 positions, that will remain same. So whatever you want to write, you can write here, suppose 7. And then here it is the position of 2, 3. 2, 3 positions. So here we can write suppose minus 6, then this will be also minus 6, and here write any element, say 8. Now we got a matrix which is of order 3 by 3. Now let us find the transpose of this matrix. So B transpose equal to what? So what we will do in the transpose of a matrix? We just interchange the rows and columns of the matrix B. So here the first row elements are 1, 3, 5. So let us write this first column elements in the first row. So that becomes 1, 3, 5. The second column elements becomes the second row. So 3, 7, minus 6. And this third column becomes the third row. So 5 minus 6, again 8. Now just compare with this two matrices. The first row is 1, 3, 5, which is same as this one. 3, 7 minus 6, which is also same. And 5 minus 6, 8. 5 minus 6, 8. So that means here we can say that B is equal to B transpose matrix. So when, now let us see another type of matrix which is known as a skew-symmetric matrix. What is skew-symmetric matrix? A square matrix capital A equal to Aij is called a skew-symmetric matrix if and only if A transpose matrix is equal to minus A, or we can say that A matrix is equal to minus of A transpose. So in other words, we can say that a square matrix capital A equal to Aij is called a skew-symmetric matrix if and only if the ijth element, that means Aij, is equal to minus of Aj for all I and j. That means the element in the ijth position of a square matrix is same as the negative of the element present in the jith position of a same matrix. Then that matrix is said to be a skew-symmetric matrix. So by definition of transpose of a matrix, we can write here A matrix, ijth element of A matrix is equal to minus of ijth element of the A transpose matrix, which shows that by definition of equality of matrices that A matrix is equal to minus of A transpose matrix, or A transpose matrix equal to minus A. Now look at here one example which is given here, shown here. So the element present in the A1 1/2th position, that is minus 3, and same element is present in the 2/1th position, that is plus 3. So they are differ by only the negative sign. So A12 element is here minus 3, and which is same as the element in the A21 position, but they differ by minus sign. So if we put one minus sign before that, then both the elements are equal. Similarly, A13 element is equal to 5, which is same as minus of A31 element, because here minus 5 is present. So before, if we multiply one more minus, so that becomes 5. So then these two elements becomes equal. And A23 element is equal to minus plus 2, which is same as minus of A32 element. And A11 equal to A22 is equal to A33 is equal to 0. So here all the elements present in the leading diagonal or principal diagonal are 0. Now let us consider the case that elements present in the leading diagonal, or we can say principal main diagonal element of a skew-symmetric matrix are 0. Now we know that all elements present in the leading diagonals having the position I and j are same. So for particular case when I equal to j, what will happen? In that case, let us consider in this case we put I in place of j, we will put I. So we get I is equal to minus of Aii, which implies that 2Aii is equal to 0, which implies that Aii equal to 0. That means all the elements present in the leading diagonal of a skew-symmetric matrix are 0. Now let us try to show that a matrix, given matrix A is a skew-symmetric matrix. We know that a square matrix A is a skew-symmetric matrix if A transpose equal to minus A, or A matrix equal to minus of A transpose. Now let us first find the transpose of this matrix by interchanging the rows and columns. So what we get here? 0, 2, minus 5, minus 2, 0, minus 1, 5, 1, 0. Now if we compare the first two columns of both the matrices, we find that 0, 2, minus 5, 0, minus 2, 5. So they differ by negative sign. So what we can do here, we take minus common from each element of this A transpose matrix. So 0 is present here. So if you take minus common, so it will not affect the sign of 0. But in case of 2, so if you take minus common, then one minus sign will come here. So let us take minus common. So that becomes 0, minus 2. This minus becomes plus 5. This minus 2 becomes plus 2. 0 remains same. This minus becomes plus 1. This 5 becomes minus 5. 1 becomes minus 1. And this 0 remain same. So now let us compare with the A matrix. So we can see that these two matrices are now same. So that we can write here minus of A. So from this example we can see that A transpose matrix is equal to minus of A, which shows that as it is a square matrix, so this given matrix A is a skew-symmetric matrix. Now let us consider a very important property of a symmetric and skew-symmetric matrix, that every square matrix is uniquely expressed as the sum of a symmetric matrix and a skew-symmetric matrix. So let us consider that let A be any square matrix. Then we can write a matrix A is equal to, we can consider a whole matrix as half A plus half A. That means we can write it as half A plus half A. Now then we add half of A transpose matrix and then we subtract half of A transpose matrix. So now this A can be written as taking half common. This becomes A plus A transpose plus, again we take half common from here. So this becomes A minus A transpose. So let us consider this is equal to P plus Q. So that means P is equal to what? P is equal to half into A plus A transpose and Q is equal to half into A minus A transpose. Now here we need to show that this P is a symmetric matrix and this Q is a skew-symmetric matrix. So for that what we need to show? P is equal to P transpose and Q is equal to minus of Q transpose. Let us find the transpose of P matrix. So if we take transpose, this half remains same. So take transpose over A transpose, whole transpose. So this will equal to 1. We know that A plus B whole transpose is equal to A transpose plus B transpose. So this property we will use here. So that means A transpose plus A transpose plus A transpose whole transpose. So we know by property of transpose of a matrix that A transpose whole transpose becomes A. So this is equal to half into A transpose plus A, which is same as the P matrix. So which shows that P matrix is a skew-symmetric matrix. On the other side, if we find the transpose of Q matrix, what we will get? Half into, just I am doing directly. So this becomes A transpose minus A. Now let us take common minus sign from here. So this minus half becomes A minus A transpose. So that is minus of Q. So that means Q transpose equal to minus of Q, which shows that P is a symmetric matrix and here Q is a skew-symmetric matrix. So which shows that A matrix can be expressed as a sum of a symmetric and a skew-symmetric matrices. Now here we have seen that the matrix square matrix A is represented as a sum of a symmetric and a skew-symmetric matrix. But in this question, there is another important part, that this representation is unique. So let us consider that the representation of the matrix as the sum of a symmetric and skew-symmetric matrix is not unique. So we consider another representation, that matrix A is equal to R plus S, where R is a symmetric matrix and S is a skew-symmetric matrix. So by property, what we can say, R is equal to R transpose and S is equal to minus of S transpose, or we can say that S transpose is equal to minus S. Now, let us find the transpose of the matrix. So what will happen? A transpose is equal to R plus, taking transpose on both sides. So this becomes R transpose plus S transpose. So that means A transpose is equal to R transpose means R and S transpose means minus S. So A transpose is equal to R minus S. So now we add this 1 and 2 equations. So what we will get? A plus A transpose is equal to 2R, which implies, because S and minus S will cancel out, so which implies R is equal to half into A plus A transpose, which shows that R is a matrix. R is same as the matrix P, which is a symmetric matrix. Now let us subtract this equation 2 from equation 1. Then what we will get? A minus A transpose is equal to R plus S minus R plus S. So here R will cancel out, so this becomes 2S, which implies that S is equal to half into A minus A transpose, which is equal to the skew-symmetric matrix Q, which shows that this Q and S are same and here P and R are same. So our assumption is wrong, that a square matrix can be expressed as a sum of any other symmetric and skew-symmetric matrix. So, which shows that every square matrix is uniquely expressed as a sum of a symmetric and a skew-symmetric matrix, and that representation is given as half into A plus A transpose as a symmetric matrix and half into A minus A transpose as a skew-symmetric matrix. So with the help of this property, we can do some questions in our next video. I hope all of you understood whatever discussed today in this video. So thank you all of you and have a nice day.